Okay, so thank you for being here. It's a pleasure to be here for the second time. This is a great venue. So the last speaker, Stefan, was telling us that it's okay to change your mind, and I just changed my mind about the way I'm showing my affiliation, because he had a very nice way to incorporate both Twitter and the Mastodon affiliation, so I didn't have time to change it, but I really liked his idea. So one thing where this talk is going to be different, for instance, from my last talk that I did a year ago, is that talk I was talking about new technology and research that we did. And today, and opposite to other talks, I'm going to talk about old technology. But hopefully it's some technology that still has a present use and might not be so visible nowadays. And it also has a future. So I'll try to convince you about that. And the topic is about peer-to-peer systems. So let's go to the term. So I took a Google Trends on peer-to-peer, and it's quite depressing. So there was a lot of fuzz during close to the year 2000, to the new millennium, and then it really faded away. So people could wonder what happened to peer-to-peer systems. So did they disappear? Was it a fad that moved on, or are they still relevant today? And I'll try to convince you of the later case that they are still used, and very much so, but they are hidden and might be interesting to recognize their role in our systems. So we'll cover the start of P2P systems, their evolution, some of the problems that they faced, and what are the current uses for this kind of techniques. So I guess we can talk about peer-to-peer systems even before the term peer-to-peer was used, okay? So the older among you might recall something called Usenet News that started in the 80s. So a way to describe it is like federated Reddit. So maybe there are better ways. So there were discussion topics, and people posted their contributions to the topic at the local server. And then there was a federation of servers that communicated with each other, and they exchanged the new information each day. So things took one day to propagate from one server to another, and it was very kind of unstructured. We can also see some components of peer-to-peer design in the DNS that, as you know, still used nowadays. So there are hierarchical components and also peer-to-peer components. And another area where there was a lot of evolution was when mobile computing started appearing, with, well, computers that were not very mobile at the beginning, but they were movable. And people started experimenting. So they had computers with Unix file systems, and they started designing variations of the file system software that could allow users to operate on their own machine and then synchronize data among different machines. So there was a lot of development in the Coda and Ficus file system. And we'll see later, these things were relevant for modern solutions of e-commerce. Some of the techniques that were developed in this decade, so in the 80s and the early 90s. So when the peer-to-peer word really appeared, was in the year 2000 probably, and it was very tied to, well, exchange of encoded music, okay? So Napster was a very famous system at the time, and although it had a brief life, just only 1 year, so I'm going to talk a little bit about how it appeared and its structure. So, when I was consuming a lot of music in the 90s, when I was in my 20s, the status was more or less like this. So people used to have vinyl records where we have hardware with some indentations on the surface, and we had analog music in a sense. But then came the compact disc format, invented, I believe, by Philips, where there was a digital encoding of the music. And the important point here is that 1 minute required more or less 10 megabytes of space to encode in the compact disc. So a compact disc had around 700 megabytes. So it was something that people could buy at the store at a rather expensive price, around like 17 euros. And then they moved on, then they listened to it. But it was not something that was easy to transmit in the networks that we had at the time. So there was a second revolution that changed everything and changed the music industry. It was the movement where we started doing lossy encoding that took into account the human hearing characteristics. So MP3 was created. If I recall, it was with the development of Fraunhofer, also another European company. So we have two European companies here doing some interesting innovation. And with MP3, you could encode 1 minute of music in 1 megabyte. And now this was compatible with the networking capabilities of the time. So people found a way to augment their music collection. So let's talk a little bit about that. So how did Napster operate? So it was a client-server system. So it was a star topology with a server, a group of servers in the center. And clients were people that installed the clients in their own computers. And what they did is they had their CDs. So they proceeded to encode the CDs into this lossy format called MP3. They registered by hand the title of the music that they were encoding, and then the software will upload this metadata to the server, and also the server had information about which clients were logged in at a given time. So people that were using the system were able to query the server about a given music, and then so for instance about flamenco music or something local, and then the server will tell which users that were online had that type of music. And then, well, you might ask, where is the peer-to-peer component here? This, for now, it's just client-server. But the technology at the time did not allow the music to be uploaded to the server and served from the server. So the peer-to-peer component was in the music transmission. It was done directly between the clients. So it was a semi-peer-to-peer system. Now, the problem was that there was still a centralized component, which was the server. So the music industry was not very happy with the idea of people ripping their music and freely exchanging the contents. So there were legal action made against the Napster service, and the service was took down more or less a year after it started. But things didn't stop there. So in a sense, this drove more evolution on the technology. So one area of evolution was the introduction of digital rights management. So like cryptographic techniques that tried to limit which users were allowed to decode a given encoded music. This ended up fading out in more recent times. But another trend that is more important for peer-to-peer systems was the creation of more decentralized approaches to this kind of technology. So the weak point in Napster was that there was a single point of failure. And then programmers developed, for instance, Gnutella, which was a fully decentralized system, almost fully decentralized. Because there is a big problem when you try to do fully decentralized peer-to-peer systems. And the problem is how you bootstrap the system. You need to know some operating node in order to connect to it. So there were still nodes called host caches that provided through probably HTTP lists of nodes that were operating in the system. So there's still this bootstrapping problem. Eventually, the music industry was very influenced by this evolution. I'm talking about Gnutella next. And they evolved to flat rate subscriptions. So nowadays, for the price of a single CD, we can pay all the music we want for 1 month, or even more. So, a little insight in how Gnutella operate. Also, another thing that we can take from the previous talk, and actually it was very good advice, that the first version of the system that you build should be simple and not think ahead of time on scalability. And actually, this was what happened to Gnutella, but in this case, it was not a good example because it took some time to adapt. So how did it operate? I installed the Gnutella node, and then I contacted a host cache. I knew some operating nodes that were online at the time, and my node will connect to random K nodes that were operating on the network. So they're trying to form a random graph. Now, once I'm connected to the nodes, I have a problem. I need to find a given content. So the content was not stored in a central server. It was distributed across the machines. So the approach they did in Gnutella was to flood the query. So flooding means that you are spreading the query across the whole network. Okay, so all the nodes that are connected to the network will potentially see the query. And you might start seeing the problems that this can lead to. So the query was flooded into the whole network up to a given time to live value until a given maximum number of hops, and any node that had the content answered back. So the problem with this is that they did not anticipate that in maybe 1 or 2 years, Gnutella will have 3 million nodes. So what happens when you have 3 million nodes that are connected at random? You get this kind of furball of connectivity. But there is still some information on this network. So I can tell you that if they were creating a proper random network called Erdős-Renyi random graph, we know some things about it. So suppose that there are 3 million nodes over there, but we know that there are short paths among each pair of nodes with just a logarithmic number of steps to reach from any node to any other node. Now, the problem is that it's not enough to know that the path exists if we cannot find the path, okay? So if you flood the network, you will inevitably find the shortest path, but you are inducing a lot of load into the network. And this led to big scalability problems in Gnutella, and eventually it evolved into a two-tier structure to solve these problems. But let's see how we can improve this and what happened in the following years. So in the real estate market, they said that location is a key. And in this case, locating data is really a hard problem in an unstructured network. So as I told you, just having short paths to your data is not enough if you don't know how to decide the next node that you are going to contact to reach the data. So it's prohibitive to explore all the paths. So the key to this is that we must impose some structure on the network, some structure that will relate, say, the node IDs with the data IDs that we want to find. And this was what happened with the introduction of distributed hash tables. So what is this bringing into the network? Let me say another way. So what DHTs try to achieve is to make sure that a node can have logarithmic information on the size of the network and still be able to, on a logarithmic number of steps, reach any desired data element. So to do that, we need to do some tricks. So this is how it is done in one of the DHTs, the cord one. What they do is, I'm a node, and I will have information about what is in the other extreme of the network. And then I will have a pointer to, so there is something else here. So there is a distance metric that is kind of saying how far each node is far from another. And that distance metric is also saying where data can be located. And when I'm choosing how many nodes I know about, I will do it in a way that I know a node that is far away from my ID on the other side of the network in the distance metric. Then I know one that is, so this is 1/2. Then I know one that is 1/4, 1/8, 1/16, etc. So this means that I will have more information about my local vicinity over here than I have about nodes that are far away. But all nodes will share this property. So this means that when I'm looking for some data, I can look at the information I have locally, and then I will see which node I need to forward my request to approach the data that I want. And first I do a long jump, and then I will progressively do shorter and shorter jumps. So this kind of started solving the problem. There are many alternatives to this, but there are still some problems over here. For instance, this is in a ring structure, and these relations are not symmetrical. So if I jump from here to here, does not mean that this node knows information about this node over here. So there was an evolution, more or less almost at the same time. And it was the Kreml system, which is already a second generation system. So with Kademlia, they solved some of the problems of the prior systems, and now the system is symmetrical. So when I receive a contact from a node, I always know that node from my table, or at least I can insert knowledge about that node. And also it allowed exploring more than one path in parallel and get the first answer that we got back. So Kademlia turned out to be very successful in the industry, from like the 10 DHT systems that were introduced at the time, and it's still used nowadays in BitTorrent, Ethereum, and IPFS. So this is one of the current use cases of peer-to-peer technology that we still have nowadays. So, okay, so we have a very sophisticated system now that we can have millions of nodes and be able to route between any pair of nodes. So looks that we might have solved all the problems, but not necessarily. So around 2007, a little bit before this, there were other problems appearing. So one of the problems is that peer-to-peer systems have a problem of quality of service. When Amazon was scaling up, it could not scale vertically, so we had to scale horizontally. And one approach was to have lots of nodes inside the data center. So to that, they incorporated some technologies from the DHT research, but in this case, they had a zero-hop DHT. So now each node knows all the other nodes in the data center so that the routing decisions can be taken much faster. So this was another of these incorporations of technology. So in the Dynamo system uses technology from DHTs, and also this technology from the 80s that detects conflicts among files. Now they can detect if two shopping baskets are in conflict or not. So Dynamo actually influenced other systems. There were evolutions of Dynamo. One is Baquero React, Project Voldemar, and the most successful one is Apache Cassandra that was also inspired in Dynamo. And Cassandra, as you know, is still used nowadays in very important players. So when you are using these systems, you are also using DHT systems. There was another problem in the genesis of these systems, and I often like this phrase here that comes from biology. I tracked it down to some author from biology, and it's like all successful systems attract parasites, okay? And from time to time, we might have parasites in our own body, hopefully not. But there's always free riders and parasites. And this was very clear in the early peer-to-peer systems. So many attacks were happening in those days. For instance, users were interested in downloading files, but once they had the file downloaded, they disconnected. So they were not providing a service to other peer users that wanted the file. There were some attempts to handle this, but not very successful, like randomizing the data within the file so that only when you get the last bit you have usable data. Other things that happened was spam. Okay, there was already spam and email. So if I'm spreading the query and anyone can answer the query, it's very easy to spam. So some nodes answered yes to everything with the content that they wanted to disseminate. And when it was not actually the content that the requester wanted. Other things happened. For instance, some of the algorithms gave more responsibilities and more visibility to peers that were promoted to super peers. And this happened after some being online for some time. So what peers started doing, since they had access to the code, was to say that they have been online for a long time and they were promoted to super peers. So actually, we are talking about a Byzantine environment, but the system was not prepared for a Byzantine environment. So there was a lack of QS and also a lack of an incentive system. And this was probably one of the reasons why cloud infrastructure also started appearing, because it was very hard to do it in a purely peer-to-peer way. We had to have the machines under the same administrative control inside the data center. So there were some improvements in this area with another trend. So this trend was very famous like 2 years ago. Not so famous now, but there's still important technology within these blockchain systems. So one important aspect is that they tackle with a Byzantine environment that is hostile. They also tackle a very important problem, which is the open membership. So if you have a close members, if you know the members of your group, you can do some kind of protocols, you can do consensus protocols, you can do many things. But if you don't know how many participants there are, you need to have a way to weight the participants. And one way in this particular system in Bitcoin is proof of work, where you try to have a quantity that is associated to each participant and that is a concrete quantity. But another thing that probably more important for peer-to-peer systems is that once you start creating these digital currencies, and if they have some value, now you have a mechanism to create incentive systems. So one of the problems with the quality of service was that users had no incentive to keep running the system. Now, if you get some credit in some monopoly currency that might have value or not, at least you were accumulating some credits and you have some incentive to cooperate with the system. So I think this is an important component that is recent that can improve peer-to-peer designs. So the experiment with quotas and reciprocity, it was not very, very helpful. And now these technologies are kind of rebuilding peer-to-peer systems, not in a peer-to-peer way. It's very hard to do things strictly peer-to-peer, but having an incentive can help now building these approaches. So how reliable can these systems be? Can they have predictable QoS? Well, we'll see. So I think there is an important evolution, but time will have to tell if we will have like really reliable systems that are purely peer-to-peer, or if we still have to rely on the cloud. So I'm coming to the end of the talk. So we have seen very briefly the legacy of peer-to-peer system developed along the last 20 years. So I've shown you which technologies, and there are many others, are still used nowadays. And so the future will tell us how the concept will evolve. So it can evolve along this blockchain Web 3.0 axis that has a pressure to use this kind of technology, but it can also evolve in another trend. So there have been talks about local first software also in the last Java on the Beach, and this is another area where peer-to-peer can be important. So I'm not the best expert on this area, but I can give you a little pitch about this. So here the idea is that the most important copy of the data is no longer in the cloud, but it will be the copy that is in your own device. And the cloud is just a backup for your data. And the idea is that even if you are disconnected, and there was lots of work on disconnected operation on the 80s, even if you are disconnected, so in a way, local first is coming back to the 80s. If you have access to your own data, you can operate over the data. So the idea is that you should not be prevented from using your machine just because you don't have a good connection to the internet at a given moment. And so when you have the connection, you can synchronize data, propagate data, but you should always be able to operate on your data. And another ingredient is to be able to synchronize with your coworkers locally, even if you don't have access to the cloud. So if you have a local network with your team members, you can synchronize with them. Another example I try to give is like I have some instrumentation to my house, and I have ways to open my my gate, okay? But this is all going to the cloud. So I might end up in a situation where I'm facing my gate, I want to open it, and I cannot do it because I'm using some cloud service that failed. Okay, this is kind of the definition of a distributed system. You can't do your work because some machine you don't know about is down. So there is a future also on this area. So if you are interested in looking at an outline of this talk, it started from a blog post that ended up in the communications of ACM. And with this, I finished my talk, and we can go to the query and answers. Thank you.